Hey everybody, thank you for clicking on my video. I really appreciate it. If you haven't already subscribed, please consider doing so. So for those that are new, what I do on this channel is I take old electronic projects from old electronic magazines and I bring them to life. I etch the board, put the components on it, I troubleshoot and I test it, and if everything works, then I put it in a case. That's what I do. So I'm hoping that interests you. Before we get going, I just want to let everybody know that I'm not that smart. I'm just a technician at the most. So I get a kick out of building these projects and I learn a lot after they're built. So, I scope it out and I check it out and I learn at that point. In any event, let's get on with today's project. All right, so today's project comes from Elektor, September of 1990. And it's an high current hFE tester. And what it does is it measures the hFE, so the DC gain of power transistors, right? Not the small ones, we want the big ones, right? So I suppose if you're building an amplifier, let's say, you want two transistors that are matched, right? And this device is going to do that. So the problem with regular small transistor testers is they only supply like maybe up to 100 milliamps or something like that, not a lot. Well, with the bigger transistors like TO3 type transistors, you need amps of current to test it properly. And so if you were to build a big tester, you would have a huge power supply. Let's say you needed 10 amps to test some of these transistors. Well, that gets pretty costly when you're building some sort of a tester with that design. So that's the problem. What's the solution? So the solution is this device. And the way this device works is it pulses current. It doesn't supply like a 10 amp power supply like I mentioned earlier. It's going to pulse the current at like a 1% duty cycle. So therefore, we just need a small power supply for this circuit. And instead of actually measuring the collector current and requiring a high powered meter with a shunt probably, what we're going to do is we're going to measure the base current. The base current is then going to be processed by a sample and hold circuit whose timing is also controlled by the same pulses controlling the collector current. And I suppose what we're going to do is then display that base current on a meter, and then we can compare it to another transistor. So we take that one off, put another one on, and hopefully we can find a match between the two transistors. So that's the very high level overview. I don't pretend to be a genius like I mentioned all the time. But that's what I got from the article. And what I wanted to do is just kind of show the schematic here. And there it is. And once again, I'm not going to pretend to understand it all. Obviously, there's the metering circuit there. And then we've got a range switches here. And then we've got a transistor under test here. And we've got two similar looking circuits here. I'm not too sure exactly what they're going to do. Maybe that's going to give us the pulses. I'm not too sure. But I can tell you one thing. By the end of this project, I probably will fully understand all of this. All right, let's get on to the build. Okay, so as you can see, I've got most of the parts. Some of them are brand new, so I do have some money into it. And the biggest part, or the most expensive, is that switch. Check that out. That's a blast from the past. So DigiKey actually has that part. I can't believe it. So I've ordered it, and let's get on with the video.
it ain't since so long. All the feels are gone. Fella stopped me on the street last night, said everything's alright. Roller coaster, make it through the day, I'm right. It seems your meal ticket is gone, but life goes on. I could never imagine something better. Yeah, right. Now you're cooking on high heat in the middle of the street.
All right, as you can see, it's done. And I was really surprised to actually find that switch. It's amazing. Anyway, what we need to do now is we need to see if there's voltages where the ICs would go. And I've got a power supply connected to it right there. And I've got about 15 volts, I think. And this is our 10 volt regulator. So that's what the whole circuit's working from. And right now I've got the meter for our power supply set to current. And I've got the current set about halfway. So it's kind of acting like a dim bulb in a way. Now, I don't have a load on it right now, but I will in 1 second. So let me turn that switch up. And there was a blip, so I'm not too worried about that. And I don't see anything smoking. And I'll turn to voltage now. So now let's look at this fluke meter. Let me go to pin 8. 10 volts for the 4066 and 10 volts for our op amp. Okay, so everything is working good there. All right, before we go any further, let's make sure that we have our voltage drops across the LEDs. So the green should have a 2.1 and the red should have a 1.8, totaling 3.9. We're going to check the actual pulse generator at this point, and we can kind of already see that we've got some sort of pulsing with the LEDs. You can see that. Let me just bring you up to the scope. And that looks like a pulse to me. So let's move on to something else. Okay, so the next alignment procedure is to build the voltage divider, which I've got here. So it's a 1K and a 1K trim pot, and adjust it so you get 2.5 volts, and that's what I've done. And then with that 2.5 volts, you inject it into resistor 30. I'm going to go to the schematic and I'll show you what I've just did. Oh, and by the way, and once you have that done, then you adjust trim pot here on the actual board to read full scale. So you can see on the bottom right hand corner, that's what you do. I'll just bring you back to the schematic really quickly. All right, the next step is to go to the 4066 chip and go to pin 13 and 12. So you're looking for a 10 volt pulse, and this is the negative going one. And on pin 12 is the positive one. So it's there. Let's move on. All right, so I think I maybe found a mistake on the schematic itself. No matter what I do with this setup, so R26 is 18K according to schematic, according to the parts list, I've checked everywhere. And then we got a trim pot, so 28K, that's our range. No matter what I do, the full scale reading is 340 microamps. So I'm overpinning the needle, which is not good. And in fact, what I've learned is when you're measuring with this device, the meter, when it's just a normal steady state, the meter will be pinned to the far end. So what I had to do is I put a trim pot in here to try to find a better resistor value. And I came up with about 79, 80K. I haven't put it in yet. I've got a trim pot on it. But then that gives me a little bit of flexibility here to actually get this to read, I guess 100% or the pin, the max. So that's what I have to do. And it works. So I will show you a quick test right now. All right, so I've got a 2N3055 connected to the tester. And it's turned on. I'm set for NPN. And I'm just going to press the button here. I think it was about 50, 52 or whatever. Now that's not the right scale. So from the actual article in the magazine, they give a scale. So I'm going to try my best to try to get that cut out, cleaned up, pasted onto this meter face too. Anyway, that'll give us our hFE. Now I have another 2N3055, and when I put that on, it actually is different because they're not from the same batch. So clearly the circuit is working. And also I tried a PMP and that worked too. All right, so I think right now what I want to do is clean up the circuit. I've got a lot of trimmer pots on there. I need to put permanent resistors in there, and then I'm going to put in a case. So let me do that, and then we'll do some real testing with the finished unit. So it's done and it looks pretty good. Now, I did attempt to do a label, like a front panel, and it was just taking forever. Some people had suggested Inkscape, and there's this other one called Galva. It's a bit tricky, and I probably spent like a half a day on both, and I just wasn't making any progress. So I just went back to the old brother P-Touch labels, and it is what it is. Look, if the label or the front panel is actually given in the magazine, I know this was actually given in the magazine, but it wouldn't fit the boards and stuff like that. So I couldn't do it. In fact, the front panel design that they gave had this board pretty much like under the meter. So this section under the meter, and there's not enough room. It just wouldn't fit. But yeah, it looks pretty good. I'm not complaining. And I don't know if I mentioned this to you, but this requires, this requires a DC adapter. So I've got one of those, and it makes it pretty breezy inside. And yeah, there you go. There's the construction. Yeah. Anyway, so let's put this on the bench. I hope to God it works. And then we'll do some testing. All right, so for those that are playing along at home, which I highly doubt, the way you would test a transistor is you would get the correct type, right? NPN, PNP, and because you don't want to have them the wrong way. And then this will give us our sensitivity, which we'll talk about later. Push to test, and then the collector current. And what I found is a lot of these TO3 type transistors, this is a TO5, I think, or something like that. They require a little bit of oomph to get them going. So usually you won't get much of a meter reading on 1 amp, so you just increase it, of course. And then, yeah, the meter reading. So the way it works is to get the DC current gain or collector gain, you would multiply the meter reading times the collector current setting times the sensitivity. And by the way, you'll notice that my scale is reversed to what they have in the magazine. I mean, you can barely see it in the first place, but I changed it around because it just doesn't make any mathematical sense to have it reversed. So 400 being there and 100 there. I mean, take, for example, let's say you had a meter reading of 2 and you had it at 10 amps. So 2 times 10 is 20 times, usually it was on the second scale from the top, so that would be 100, right? So what 2 times 10 is 20 times 100 is 2,000. My God, that's ridiculous. 20 times 100, yeah, it's 2,000. Anyway, so it just didn't make sense. But when you reverse these scales here, it's actually correct. And or you get a more reasonable value. I don't know if it's correct, but you get a more reasonable value. And anyway, when you have a transistor on it, you push the test button and then you get your meter reading, and away you go. All right, so let's get down to some testing. So I've got 2 of these RCA 40250 transistors. I know you can't see that. Anyway, but the same date code, so they came from the same device that I scrapped. In any event, I've got it preset now where I'm at the times 4 scale. That gives me a reading of a, reasonable reading in the middle. And I've got 2 amps. And by the way, when you're at 1 amp, you don't even really get a meter deflection. You get a little bit. So you have to increase the current. I think these bigger transistors require a little bit of oomph to go through them. In any event, so I'm reading 3. So the way you calculate it, like I said earlier, is 3 times the collector current, which is 2. So that's 6. And then you multiply by the sensitivity 4. And that gives you 24. hFE of 24. It's kind of low. When I look at the data sheets, it's minimum 25 and a maximum of 100. Collector current, DC. So that's with this transistor. Now let me quickly put the other one on. And what do we get? We get a loose connection here, I think. There we go. So we get about 2.5. And so when you do the math there, it's 2.5 times 2 times 4 is 20. So a little bit close. It's off by 4. So again, it's very low for this transistor according to the data sheet. So what I'm gathering is something's not correct, I think, right? You know, when it comes to the scaling and whatnot. I mean, again, we're having fun here. This is just fun. So like meter scale, I'm not too worried about that. And in fact, I think what I'm worried about is more to get a matched type of a transistor, right? So that's what we're aiming for. Yeah, I know I got 24 on the other one. I got 20 on this one. Kind of close, but that's the whole intent for this transistor tester, is to get something close. I suppose another intent was to actually have an accurate reading, but I'm not getting it. Yeah, let's do one more test. All right, so I want to test the PNP transistor here. It's a 2N5875. And the first thing you notice that is I got the right switch selection here, PNP. And the next thing you'll notice that the meter scale is not at 100% all the time. It's actually at the very bottom. So it's reversed to what the NPN is. In any event, I left the same settings as before. I'm at the ×4. I'm at 2 amps. Let me hit the press to test. So it looks like I'm getting about 3.5. So 3.5 times 2 times 4, that gives us 28. So a DC current gain of 28. Seems reasonable. I checked the data sheet. The lowest is 20 and highest is 100. So yeah, so it's not the greatest, but it's a reading. All right, so I still have the PNP transistor in, and let me hit the press to test. And yeah, I know it's hard to see. It's 3.5 still, which is great. I just wanted to show you what happens with the sensitivity when I adjust that. And you can see the scale going down, right? Which is good. So I see a good relationship. Now, as far as the math goes, I don't think it matches up completely, but well, let's just quickly do it. What do we got? We got 1.8, let's say. 1.8 times 2 amps times the times 1 is equal to 3.6. So how can I have a gain of 3.6 when on the other scale, I had, you know, what was it? 28, I think, right? So I see a discrepancy there. Anyway, let's go back to the ×4. And when I increase the current, it doesn't change, right? So there's 10 amps. So I still get 3.5 reading. Times 10 is 35. Times 4 is 120, almost 140, right? So again, the hFE doesn't change. Now, or sorry, the hFE does change by a lot. And so I can understand the hFE not changing when it comes to this scale here, because, you know, I get it to conduct basically at 2 amps. Well, you would think the hFE should stay the same through the whole range, right? In practical sense. But the math just doesn't work out. That's really what I have concluded. And speaking of conclusions, I think I'm going to end the video here. So I can say that this meter is great when you want to try to find a matched pair of transistors. And they even mentioned that in the actual beginning of the article, so that was maybe the real intent of it. But as far as hFE goes, it's probably not that accurate. I could be wrong. Maybe somebody can explain it to me, but just like I said, looking at the scales, forget about any transistor being on there. Forget I even built the circuit. Just pretend I had this faceplate here like that. And it was 400 times worse, actually, when I had it according to what they had in the magazine. So I just don't see the math working out. But I had a heck of a lot of fun building it. Again, I'm learning so much as I go along, and I'll add this to the bench. And like I said, if I want to match some power transistors, well, this will do the trick. So thank you for watching. I really appreciate it. Take care and bye for now.